Welcome back to After Hours Engineering. In this episode, we're going to switch gears from working on the Toolchain workflow to building the foundations of our processor, the A09. More often than not, that design begins with the instruction set architecture, the ISA. It defines what a processor is capable of. We'll begin by defining a very minimal yet functional set of instructions, totaling 11 plus one pseudo instruction. So let's begin by defining that ISA. Let's design an ISA that both simplifies the instruction set and limits the overall complexity of the processor itself. So I'll paste in what I think the ISA limitations will be. We're going to limit it to 16 bits, just so that it easily fits within any FPGA you choose to use. For simplicity, we're going to limit all instructions to a form of inherent addressing. This will simplify memory management alignment because all instructions take up exactly one word of memory, and it simplifies the instructions themselves. Inherent addressing is where an instruction specifies everything that needs to be done. You don't need any additional following memory locations to help specify the instruction. Inherent is pretty much the simplest format for instructions. We're also going to limit our data calculations to the lower 8 bits. The upper 8 bits are ignored except for internal sign extension. The reason for this comes from our inherent addressing. Because we only have 16 bits, a portion of the instruction is designed to tell us what code we're doing, like an add or a subtract, which leaves us only with pretty much the lower end of the instruction. In this case, I've arbitrarily clamped it to 8 bits, which is okay. We're just building a simple processor. Also, I'm only connecting up 8 bits of data to our LED panel. And because we're limiting our instructions to immediate address mode, we will automatically be restricted in what we can load and or address, meaning the lower portion of the instruction can only hold 8 bits. A little bit more, but we'll keep it to 8 bits. And finally, there'll be a total of 11 instructions, plus one pseudo instruction. So what are these instructions? Well, I've broken them down into 6 categories. This is our instruction set, and I've tried fairly hard to limit it to just these 11 instructions plus one pseudo instruction. They're broken down into categories. We have a no-op, which basically does nothing but consume an instruction cycle. We have our arithmetic logic units. The subtract and the compare are identical except the destination is ignored during a compare. We have our branching instructions and jumping, a load instruction, our ability to take one of the registers in our processor and output it to the pins on the FPGA, halting, and then finally resetting, and a move register to register instruction. This is a pseudo instruction because internally we'll see later on that it's actually just performing an add with a 0. And that's it. That's our 11 instructions and one pseudo instruction. Now, even though the ISA is small, it is still quite capable of handling complex programs. Let's take a look at the instruction formats. Every single one of our instructions will follow a very specific format. The upper 4 bits will always represent a code that the processor will recognize. Internally, which we'll talk about later, it's routed to a decoder inside the sequence control matrix. The next set of bits is generally the miscellaneous bits, and only one instruction really notices that, and that's the subtract/compare. The remaining bits are specific to the different formats that we have, and in this case, this is the register format. So we'll bring that one up next. Again, the upper instructions are bits are the instruction itself. Like as an example, this could be the add instruction, of which there would be no control bits, and we never will have any control bits used in the register format. And then the rest of them specify the operands for the instruction itself. So if this is an add, Then these two sources specify the operands, and this specifies the destination of the results. Next is the branch format. This one, we only have one instruction, and it's the branch on not equal to 0. So this is only one number. It doesn't require any control bits, and it specifies the address that we will branch to in only 8 bits, and it's signed, which means we can only branch forward or backwards in memory by 127 bytes. Then we have the load and store inherent format. This instruction, again, is only one of them, and it has one number. It uses no control bits, but it does specify a destination register that we are going to take the value that's embedded in the instruction itself and load it into the destination register. And then finally we have the inherent format. This is the simplest of all the instructions. An inherent instruction means that the instruction itself needs nothing more than the code. The processor knows what to do when it sees that code. An example would be a halt or a reset. Now that's it. That's all the formats that we'll be using in our processor. Very basic and very simple. Knowing the format, let's take a detailed look at each instruction and see how they are formatted in both binary and hex. We'll start with the no-op instruction. It's the simplest of all. Its code is 0001, and it's an inherent instruction, meaning it takes nothing else in order for the processor to understand what it needs to do. If we were to write out the 16 bits of instructions, that would turn out to be 100 in hex, and its assembly instruction is no-op. The add instruction is more complex instructions where we are taking two operands, S1 and S2, adding them together and placing them in the destination. Its instruction code is right there, and it has no miscellaneous bits that it needs, but it does need the lower 9 bits to specify. This is what it looks like in assembly, and this is the instruction as we would put it together into its binary format. And this is the equivalent hex value. We have a 2, we have a 0, we have a D, and then a 1. The subtract instruction is the most complicated of all the instructions because it can actually act like two different instructions. With the subtract, we are looking at taking the two operands, S2 and S1, subtracting S1 from S2, and placing it in the destination. However, one of the control bits does specify whether this is a subtract or a compare, and the only difference between the two is that on a compare, we don't care about the destination. So I have two formats of the instruction. For a subtract, we are looking at subtracting R1 from R2 into R3, and that's a subtract flag. And you'll notice that the control flag is a 0 because we do want to store the data into the destination. If we specify a compare, this control bit becomes a 1. That's it. This is the compare instruction. The next instruction is the shift left and shift right. The way this instruction works is that S2 register contains a number that tells us how many positions to shift to. So you would load the S2 register, let's pretend it's the R2 register, with a specific number like 2. You would load the R1 register with the number that you're going to shift. This way we will shift whatever's in R1 two places because we loaded R2 with the number 2. The shift right is identical. The only thing that changes is the instruction. That's it. We have our instruction code, the 3 different registers specified, and that's it. This is the assembly representation of it. The branch not equal is a relative branching instruction, and it tests the Z flag or the 0 flag to determine whether it's going to take the branch. In this case, if it's a 1, it will take the branch. If it's a 0, it will not take the branch. The Z flag is generally set by some previous processing instruction. But what address does it branch to? That is specified in the lower 8 bits in signed notation, which means it can only move forward or backwards in memory by 128 bits. In assembly, we might specify it as a -3, but in binary notation, we would express it in 2's complement form. That's the branch on not equal. It is a relative branching address. The jump instruction is very similar to the branch on not equal. The only difference is that it doesn't care about any specific ALU flags. It just takes the jump regardless. However, in order to specify where it jumps to, you have to load one of the registers prior to it with an address that it is going to jump to. You specify which register that it reads in order to get its address. You can jump all over the memory using the jump instruction, but in this case you can only load it with 8 bits based on our load instruction, so you technically can only jump forward 256 bytes, but you can't jump backwards. Again, we're just keeping the processor simple. The load inherent instruction is a fairly simple instruction where we specify what we want to load into a register directly in the instruction itself, and we specify where we want to load it based on these 3 bits. So if we want to load R1 with the value 0B, we make sure that our instruction here says 0B. It's a very basic instruction that again fits in one word. Simple, just like we like it. The next instruction is technically a specialty instruction, where we use it to see what a register value is on the outside world. It's specifically designed to send its values out of the CPU so that you can access it from a top module. It's pretty basic. This is the instruction code, and then what register we want to expose to the top module. We specify it in the lower 8 bits, and that's it. It's very handy when you want to see what the processor is doing after it's made some sort of a calculation, like added 2 registers together. The halt instruction is another one of the inherent instructions. It's a very simple. The code itself tells the processor exactly what it needs to do. And in this case, it abruptly halts the processor. Nothing else happens. The only way for the processor to resume operation is by issuing a reset. The reset instruction is the last of our actual instructions, and again, it is another inherent instruction, meaning the code specifies exactly what the processor needs to do. We need nothing else following it in any of the other bits. In this case, it will immediately stop whatever the processor is doing and send it back into the reset sequence. And that's what this instruction does. The only other way to cause a reset is to trigger the reset pin, to say, for example, bring yourself out of the halt condition. Our final instruction is actually not an instruction in and of itself. It's really an alias for another instruction. And in this case, it's the alias for the add instruction. The way it works is that we want to move a value from one register into another register. One way to do that is to silently add a 0 to the register that we're trying to move data from, and the result is sent to R2. Any register with a value of 0 added to it leaves the register as is, but goes into the destination. This is literally the equivalent of a move. And internally, the processor is going to use the R0 register, which is a constant register. It has no other value in it but 0. If you try to load a value into it, the processor will just throw your value out the window, and R0 remains as the value 0. So that makes this instruction a pseudo instruction, because in reality it's actually doing an add with a constant 0. And that's the last of our instructions. Our instructions use only one of the most common ALU flags, the Z flag or the 0 flag. However, our processor implements 4 of the most common flags just for completeness. And as we've seen, some of the instructions are sensitive to this flag, but which ones modify it? That would be the ALU instructions, and we have 5 of those: add, subtract, compare, shift left, and shift right. Before we wrap up, let's take a look at a small snippet of behavioral code for determining the Z flag after adding 2 registers. Let's imagine we have 3 inputs: the ALU flags from any previous operations, 2 register inputs A and B, and a carry flag for completeness. In Verilog, you can describe the add operator in many different ways at the gate level, transistor level, and even higher in the behavioral level. And that's what I'm doing here. In that case, you literally define your add operation as we're doing here, as if you were programming it. A plus B plus a carry flag. We take that information and we concatenate it together to form a carry flag and an output results. However, we only want the output of the add, and we want that so we can compare it to the 0 value. That is actually what sets our 0 flag, or our Z flag. So any operation, behavioral in this case, can be transferred down and compared to some sort of value or another behavioral structure and calculate a flag. And that's what we want. And that will take us into the next episode, where we will design, simulate, and synthesize an arithmetic logic unit, or an ALU. So until next time,